Hi everyone. We are happy to have Hector from Harvard University, who's going to talk about S-duality in 4D and higher dimensional string landscape.
Thank you. Thanks a lot for the invitation to speak here. I'm going to be talking about the work that I'm doing in collaboration with Hector, who is now a postdoc at CERN. And the motivation for this, the problems that I'm going to talk about can be contextualized, for example, in the Swarm program. That's one angle that I'm going to use. When you ask a question, a very general question, which is what is the space of effective field theories that can be consistently coupled to gravity? If you are working in this program, you make some conjectures about what are general properties of gravity. But it's true that since string theory gives you a consistent vacuum of quantum gravity, then they should satisfy it. There's perhaps a stronger conjecture, you don't have a stronger idea, which is that the vacuum of quantum gravity in general are given by string theory. Yes, that's not the string Lampos principle. And you can test this idea with a high degree of precision if you study very symmetric configurations, very symmetric vacua in string theory, quantum gravity in general. In particular, if you have a lot of supersymmetry, not maximal, but a lot, 16 supercharges, then you can really test this with very strong results. And this was the basic idea behind these two articles by Yuta Hamada and Baja, and then later by Bedroya, Hamada, Montero, and Baja, where they studied 8-dimensional theories and 7-dimensional theories and trying to recover the data that is encoded in string theory just from the bottom up, using some conjectures in the Swarm program. Now, this is very good and well. This is a motivation for looking at these theories as some kind of laboratory. But I want to point my attention to the problem of classifying such theories, which is in fact a much older problem. It's a classical problem in string theory. And so there's a question you can have: do we actually know all the vacua that we can have in a certain regime, like with this much supersymmetry? I would claim that in 7 dimensions and higher, we have such a complete knowledge, although to prove this rigorously it's very difficult, but I would say there's very good evidence for this. Yes?
Naive question. I'm
Yes.
not sure I understand why these proves the Lampos principle. Why are these tests of the Lampos principle?
Okay, so it's not a full proof of the Lampos principle. If you wanted to prove the Lampos principle, well, I don't know how to do that.
Why is this tests of Lampos principle?
Why is this a test? Well, because you are doing some bottom-up construction, and then what you see is that if you have you establish some hypothesis, you are able to recover the fact that that theory is going to be given by, for example, M theory on a K3 manifold. Okay. So
why does this test quantum gravity vacuum equals to string theory vacuum?
I didn't say that. I didn't say
Isn't that the principle? That's the principle.
No, the principle is not about test. The principle is just a relationship. Let's say quantum gravity is going to be string theory. Okay. Now, a test for that is saying if you forget about string theory and you do bottom up, are you able to say, oh, everything that I can get is given by string theory? That would be a proof of the string Lampos principle. In that regime, yes, like for 7 dimensions and this much supersymmetry.
But if you cannot get it from string theory, well, what does it disprove?
Well, but there's no example of that.
I mean, it's only a test.
Well, if you were able to do it, you would disprove the string Lampos principle. So then that would be the end of it.
But maybe that's not quantum gravity vacuum either. I mean, I thought the principle is a string theory vacuum equals to quantum gravity vacuum.
Yeah.
So low energy theory may not be in the quantum gravity vacuum either.
You're assuming that you're in the quantum gravity vacuum. That's why you're imposing those constraints. Yes. If you have something that is not in quantum gravity, then it's not going to be given by string theory. It's outside.
In order to test that, wouldn't you have to know what is the quantum gravity vacuum to begin with? Or?
Yeah, sure. You're starting from some EFT that has gravity and has some properties like some gauge group, some content. Yeah.
But maybe it's not in quantum gravity vacuum anyways.
Yeah, but you're starting from that assumption because you're assuming that it's satisfying these principles. Yes, and then if you see that that's a string theory, that already tells you that's quantum gravity because it's coming from string theory. So maybe I can clarify on that there. But we can forget about this for the moment. This is just a motivational framework for a top-down question, which is what is the space of vacua? And that's a much older question. And then I'm interested in that question because then you can say, oh, I find something new in string theory that was not accounted for in these conjectures. Maybe I can violate one of those and I can refine this program. So that's kind of the spirit here. And the point is that in 7 dimensions, you may have a complete picture, okay, but then in 6 dimensions, this is no longer true. And there's a lack of knowledge there. Now, when you have 6 dimensions, you can reduce the amount of supersymmetry to 8 supercharges. That's what most people would do because then you have a richer physics. But still, you could keep your 16 supersymmetries and see what else you can get. So that's kind of the idea here, and then try to go to 5 dimensions and so on. The point here, I say here, there are think of this vacua that you have as being arranged in theories or moduli spaces. That's what I'm going to be talking about. And in 7 dimensions, you have 13 of them. And then if you go to 6 dimensions, you have 4 more. And this was the state of knowledge, let's say, up to 1 month ago. These 4 theories are explored in these 2 articles. And then I'm going to mention some new results along these lines. So what I'm going to do now in the rest of the introduction is just go over what I'm talking about, what are these moduli spaces, how they are realized, and things like that. This is inevitably going to use some constructions, some particular constructions in string theory, like I'm going to talk about F theory and so on. But then I will say that that microscopic construction is not really that much relevant for what I'm going to be talking about, which are more general features of this vacua. Okay, so bear with me for the moment. The first point is that those theories that I mentioned, these 13 theories, in 7 dimensions, you can realize them in a kind of universal frame. So in string theory, you have different duality frames. You can use a perturbative construction. You can use a geometric construction. And some of those are special because they allow you to reach all the moduli spaces, or to put it in a different way. If you have a quantum gravity vacuum, then it would be true that it will admit a description in these terms. So in 7 dimensions, this is the case with the F theory, which is a 12-dimensional theory. And you say, I have an internal space, which is 5-dimensional. Those geometries are given like this. It's our smooth manifolds. There are quotients of a K3 surface times a circle, or a T4 times a circle, where you are fibering a T4 over a circle, or fibering a K3 over a circle, with some monotony with certain order. And these are these 2 possibilities here are geometric. Okay, but also you can have more subtle things where you take one of these constructions and you turn on a discrete parameter. It's called a discrete theta angle, and that gives you an inequivalent theory. It has an inequivalent spectrum and so on, and you do your accounting and you get this result. Okay. So these ones were studied systematically in this article by the Warren Company in 2001, although there was some previous work on that in the 90s, of course. And then these 3 theories were constructed by me and Miguel Montero in 2022. But the question is, let's try to go further, look for something more general. But the state of the art at that moment, when let's say a month ago or something like that, so there are 2 more theories. So you can compactify these theories on a circle. That certainly will give you 6-dimensional theories. You can also construct new ones that are available in 6 dimensions. And these are non-geometric. They are constructed by so-called orbitals, asymmetric orbitals. They're non-geometric constructions. They're stringy. You can take a heterotic string on T4 and with some operation on that, or a type 2A string on T4 with a set 5. Now, there is some piece of data that distinguishes these theories. However, they're different. Well, there is, when you have 16 supersymmetries, the only thing that you care about besides gravity in some sense is gauge symmetry. And your gauge is going to have some rank. So you can have a theory with maximal rank in 7 dimensions is 19. And then as you look at these other configurations, you have different ranks that they become smaller. And in 6 dimensions, something special happens, which is that rank here, it can become 0. That's and it will have the consequence that the theory doesn't have moduli except for the string coping. So okay, this is favorable because if you reduce the rank, you're approaching rank 4, let's say, which is the rank of the standard model. But in any case, this is a distinction between them. Now, this is the main point of the talk, the main idea of the talk, around which everything else revolves, which is that if you look at the spectrum of those theories, if you look at the massless spectrum, if you look at gauge bosons, you can construct special maps that connect them. So here, this is an example in 9 dimensions. There are in total 5 theories, there are in total 5 components of the landscape, the modulized space. And here in blue, I just give some realization that this is just a name for those theories. And this number here is the rank. Okay. And the statement is that if you know the spectrum for the highest rank component, you can define a formal operation that will act on it, that will act on the gauge group, and it will reproduce the spectrum of any vacuum that you can find in all of the other theories. Now, you can systematically obtain these maps now. These maps are realized microscopically. If you study your backgrounds, you can see relationships between them that will give you a microscopic explanation for why this thing is true. But you can also do it from an abstract point of view. There are quantities in these theories that are protected. They are invariant. They don't really change if you tune your moduli. And if you study them, they tell you what are the gauge symmetries of those theories. And they tell you how you can relate these theories amongst themselves. And that abstract construction, it can be generalized across dimensions, which is very important because as you compactify a theory to lower dimensions, then the space of vacua, it gets larger. So if you have more components, so if you have a general map that relates to them, it has to change. It has to account for the fact that now it's giving you more things. And you can really do that in an abstract way and obtain a map that works in 6 dimensions and a map that works in 5 dimensions, not in 4. I mentioned that at the end. So, but since our knowledge kind of stops in terms of completeness in 7 dimensions, we would like to understand 6 dimensions. And this abstract construction is something that I explore with a colleague, Freitas, in 21, and we reconstruct that map, and then later on try to use it really to classify every moduli space, and to argue that it actually produced new theories, that it gave rise to the expectation that there would be theories that were not known before that. So this is like the central object of the whole program, like having this map, trying to understand that map, where it comes from, and so on. The main features of the map in 6 dimensions are as follows. So in total, you have 23 rank-reduced theories. So you have a total of 24 theories in 6 dimensions. At that moment, 16 were known, 7 were new, and it also predicts theories with discrete tangles, with this discrete parameter, which is a non-trivial thing because that's something that is non-perturbative. So you could say, oh, maybe this map has some perturbative explanation. Well, it doesn't because it's predicting something that is not perturbative. Then you see that this is the rank reduction that you can produce with that map. And if you say, well, these are all the theories, then it's telling you a statement about what are the consistent ranks that you can have for gauge groups in quantum gravities with this much supersymmetry in 6 dimensions. You don't have odd rank, for example, and then you can ask, is there a fundamental reason why this is not possible? I don't know. Is there a fundamental reason why you cannot have odd rank? I don't know. So that's still an open problem, but I want to just point towards 2 puzzles that arise when you have this map. And the first puzzle is, it has to do with the classification of chiral conformal field theories in 2 dimensions, with central charge 24 and 12. So the idea here is that such theories with central charge 24 were classified by Chelekens in 92. And then in 17, Gerald Hahn, a mathematician, he noticed that all this map that we found here in 6 dimensions, it's already there in many other contexts. But he noticed that if you use exactly that map, he could recover the classification of theories with central charge 24. Yeah, so it worked in a very similar way. Something that he didn't emphasize very well, or he didn't really emphasize at all in that paper, is that if you use that map, you would also obtain some currents of theories with central charge 22. Central charge 12. Okay, and that actually has a nice explanation in terms of string theory. The reason why this map is appearing here is because there is a relation between this classification and string theory, and that's the first puzzle. How does that work? But the main puzzle that is the topic of this talk, what I want to emphasize, it has to do with the nature of the map. What's the physical nature of the map? And the first point is that the map, it acts on gauge groups. And in 6 dimensions, it can only act on a gauge group when it is non-simply connected, instead it has a non-trivial topology. This gauge group here is spin 32 mod set 2. This is the fundamental group of this gauge group. Is the one that appears in 10 dimensions in one of the heterotic strings. And here's a schematic form in which the map acts. It defines a rule in terms of the data defining the gauge group, which in this case is a linking diagram. And it spits out this spin 17. And that's what you get. And there is a theory with spin 17 that is consistent. But why? So this is a formal thing. What's the physical realization? That's the second puzzle. Now I just want to give you a summary of the results. And I'm going to advertise and broadcast the solution to the first puzzle, which is the content of this my last paper that I had with Can by Parra, who's a grad student at Harvard, and with Huri, who is here. What we managed to do there was prove that there is a relationship between closed perturbative heterotic and type 2 strings, system supercharges, in this regime, six dimensions, with those bosonic and fermionic CFTs in a rigorous way, like try to say we match the construction of those theories that establishes that relation that we seek. The new theories, we construct them systematically. Explicitly, there are new theories of type 2 strings, and there are also new theories of heterotic strings. We don't do that systematically. That was actually the subject of a different article published by Andres and Sade in January this year. And so we have a full picture of 6 dimensions at the perturbative level. And also with discrete angles, we also did that in this article. So please, if you're interested, you can look at the article. What I'm going to talk about here is the solution to the second puzzle, which is the physical realization. And really, I don't have to spend much time on explaining what's the solution to the puzzle because it's remarkably simple. So I will do it at the end, after I give the necessary background. But the upshot is that there is a procedure that you can apply physically that doesn't depend on the frame that you're using. You can even think in some sense of this as just quantum gravity. You just care about the spectrum of your theory and topology of the gauge group. And that gets you a long way to formalizing how this map acts with some subtleties that I need to explain. The nice thing about this is that it relies on strong weak coupling duality in 4 dimensions, like Montone Olive. So it's manifested something that's non-perturbative. Okay. And besides, it generalizes to dimensions 9 to 5. It gives you an explanation for why you had these reduction maps in 9 dimensions down to 5, and it manifests breakdowns in 4 dimensions, which is signaling something new there, which might not be unexpected because in 4 dimensions, gauge dynamics become more complicated. So I'm going to give you a review so you can get the context for how all of this works. Just a review of lattices, gauge groups, and fragment reductions, and things I haven't mentioned, explain them. Then I'm going to tell you how you get this map in 6 dimensions and what is the actual physical realization. And besides that, I'm going to make just a few comments. In other dimensions, I'm going to explain in some detail, if I have time, how it works in 9 dimensions, which is an instructive example. And then some comments in Outlook and what can we do with this from here on. So first, this is an gauge group. This is some basic aspects of string theory. Although I emphasize that you don't really need to think about the microscopics, but the microscopics of string theory give you the tools that then we will abstract out. Okay, so we start with heterotic strings, and heterotic strings give you the foremost example of theories with 16 supercharges in 10 dimensions. And then you simply need to compactify that thing on a torus. You need to take as an internal space a torus. It's a flat torus, it's nothing too fancy. And once you do that, now you have massless fields in your theory that define your configuration. You have the metric field, you have the B field reduced to cycles, and you have Wilson lines along those cycles coming from your gauge group. And famously, this is the Supol-Narayan moduli space, which is just a coset. So it takes the form of a coset. Locally, it looks like this. Then there is a global description of that space that is given by a discrete subgroup, which is the group of automorphisms of some lattice, but this as some discrete group. And it will tell you what are all the possible symmetry enhancements. It will tell you all the data that we actually need to define this mass. Then, as for the nature of the moduli spaces themselves, say you have different connected components. They have this structure where if you turn on your moduli fields arbitrarily, you have an abelian gauge group. The rank is not changing, so it's just U1s with the appropriate rank. But when you go to special subregions of this space that are actually walls of a fundamental domain with a few degenerates, you have symmetry enhancements. Okay. In 9 dimensions, the situation is very simple because you can encode this structure completely in these kinds of diagrams. These are Coxeter thinking diagrams because this thing mathematically is a Coxeter polytope. And these nodes here are telling you what are the walls of the fundamental domain, and the way in which they are connected tells you what are in what way they intersect. So when you go to one of those walls, you get an SU2 symmetry enhancement. And then if you intersect those walls, you have more and more enhancements. So everything is encoded here. Say you take a subdiagram here, like that, and you have, you will identify, you need to identify that this is a diagram that corresponds to an E8 group, and that corresponds to an E8 group, and this corresponds to an SU2. That tells you there is a point in this moduli space where this is the gauge symmetry. You can take another subgroup, and like this, that tells you, oh, there's an enhancement to SU8. So in that sense, the problem is solved given those gauge symmetries. But more generally, if you want to solve the problem in lower dimensions, you need to use more sophisticated techniques. You need to use a general staining, which is that if you look at the Narayan lattice, as I said, this lattice encodes the global structure of your moduli space, and therefore it encodes on all of these walls and all of these enhancements. The data of the enhancements is completely encoded there if you look at embeddings of weight lattices of groups. If you can show that a weight lattice admits an embedding of a certain type in this lattice, then you say this gauge group is going to be realized physically. So it will have some roots, it'll give you massless states for gauge bosons. And the other data is going to tell you about the topology, which is going to be relevant later on. And so, for example, there exist these embeddings where you have the weight lattices of these groups. You can show that they're embedded here in 9 dimensions, so you recover the same statement that you have these enhancements. But then you ask, can you do actually a classification? Because this is just a statement of, okay, you can construct them like this if you find them like that. And this has been known for a long time. But can you do a systematic classification of that thing? Well, systematic classification, I don't, it's a strong word, at least in this regime. But there are algorithms that allow you to systematically explore these kinds of embeddings, which have application to many other setups, but in particular here it works, and so you get a bunch of gauge groups. And then after checking with other methods, one can see that this is a complete procedure. But the upshot is that we have methods to classify these gauge symmetries. Now in 6 dimensions, the situation is actually easier because there are theorems that tell you, oh, if you want to have a lattice that embeds into gamma 20,4, which is relevant to the dimensions, that's equivalent to a statement that the lattice embeds into another lattice. Now, this lattice here is not Euclidean. This is an indefinite lattice, signature 20,4, so the problem is kind of out of control. It's there's no finite way of encoding these things. But if you look at Neumeier lattices, the situation is different because these guys are Euclidean. So we're transforming an indefinite problem into an Euclidean problem, and it's very easy to do the classification for the Euclidean problem because they are encoded in these diagrams again. So these are some Dinkin diagrams. The idea is that you start with a Dinkin diagram associated to one Neumeier lattice, and you delete 4 nodes in any way that you want, and you're going to get a geisha that is physically realized. But these are some examples.
Yes.
Yes.
Is there an intuitive way of understanding why this happens in 6 dimensions once you get to gamma 20,4, but not higher?
Yes, the underlying reason why this is happening is that there is a kind of operation that reflects the 4. And so you have 20,4, you can relate it exactly to 24. And so let's see. That's a very abstract intuition, sorry.
Something like
It's like take the CFT, for example. Take the CFT in 6 dimensions, and it's going to have left moving and right moving part. And then you can formally take the part that is right moving that has the associated to the 0,4 part, and you can reflect it. So you can change the signature of that consistently all the time. And that's going to give you 24. Now, if you try to do that in higher dimensions, then you have 19.3 and you get something like 22. That is not, there is no even S-dual lattice with that signature. Yes, so it's not even something that is well defined. And so, for example, you can do this again in 8,24 if you were trying to characterize 2-dimensional enhancements. You will have a similar statement, but now you have to look at C=32. Euclidean lattice with signature 32, so you can play that when you have like a 4 and an 8, something like that.
But could you not just drop all the way down
and then go up?
Yeah, they go up.
No, because the problem is that lattices that have signature 32, they are the number of them is it blows up. So if, for example, here I can give you this picture, and there you have all the Neumeier lattices, and from that you get all the data. But if I wanted to show it with C=32, then there would be at least what is it? There's a lower bound for the number of lattices, which is like 40 million. So the problem really blows up. But you can do it in principle. So 6 dimensions is really special. Because of this, and also if you look at more refined data, you can get the topology of the geishas. Okay, and so you have a full characterization of these things. Now, why? Well, this is going to be important for rank reduction. So the simplest example of rank reduction is given by a perturbative string, which is the so-called CHL string in 9 dimensions. And as I said, there are these maps that lower the rank, but they have a microscopic realization. So here it's very simple. You just take your CFT that has currents for E8 and E8. You put that thing on a circle, and then you perform the operation that goes around the circle, half period shift, and you trade the E8. So you are turning on a holonomy on a circle. And so that picks up the diagonal E8 and gives you a consistent theory with reduced rank. The moduli space now looks like this. All of the moduli spaces with 16 superchargers are going to look like this. The only difference now is that you have a different rank and you have a different discrete structure. Now, this lattice is not subdual, the narrowness is subdual, but what that means at the end of the day is that you are losing a constraint on the lattice that before it was simplifying things. But now this funny lattice is allowing you in some sense new physical phenomena like different gauge symmetries that you couldn't have before, and things like that. So that's just to make the point that each one of those moduli spaces really is not just the same old stuff, let's say. So, okay, this is what I say. You can have symplectic groups, you can have spin 2n+1 groups, you can have F4. These are non-AD. But still, the group data is encoded in some Euclidean lattice of this charge, of this momentum lattice that was computed by Mikhailov a long time ago. But the rules of how you get gauge symmetries, they change, they become a bit more subtle, precisely because you don't have a set lattice, but this was worked out in this article. But the key observation of Mikhailov that really makes all of the following things work is that you can always, well, not always, but down to 5 dimensions, you can embed this lattice, this one, this gamma CHL, you can embed the data of the theory, the lattice, into that of the Narayan, of the full rank. Okay, so this is just an example. This is the Narayan lattice in 9 dimensions. This is an even self-flow lattice of signature 1,1. This is E8 and C8, and this is the CHL. This is a very simple embedding, and obviously, the difference is an E8 factor. Oh, and then you say, well, I can embed the weight lattices into each one of those. One realizing a gauge group in one theory, one realizing the gauge group in the other theory, and then you can make this association. And that is what is going to allow you to define these ranks, these rank reduction maps in an abstract way. You can simply invert, you can go from CHL here to Narayan, and you can have one embeds to the other, and then just invert it. And then you can go from Narayan to CHL. Yeah. The story changes a bit when you go to lower dimensions because the lattices don't change in the same way. Narayan is just extended by gamma 1,1, and the CHL1 is extended by gamma 1,1 too. So the way in which these things embed into each other is not trivial, right? But still, you can define a map, and because of this fact, the map is going to change. And so before the map was takeoff an E8 factor. Here the map works a bit like this. You have some spin group, some orthogonal group, and it's going to become a symplectic group. And in fact, there is a microscopic, for those who know, there is a microscopic description of this thing, like locally in terms of gauge theories, in terms of orientifolds, so-called frozen singularities. Like you can trade, you can transform one stack of orientifold planes and D-branes into another one that is a bit different, like turning on a flux, and that physically realizes the map. You can go in 7 dimensions, the map is going to change again. You have something like that. Now you have 2 groups, they transform into symplectic groups. There are other possibilities, more exotic, like you can get F4 groups from E8 groups. And then the picture that I had before with the orientifolds is going to generalize in 7 dimensions, going to generalize to a different setup, which is M theory on a K-tree manifold with frozen singularities. So I'm not going to explain in detail what frozen singularities are, but the upshot is that gauge symmetries in these theories, they come from singularities, from geometric singularities. And if you turn on fluxes on those singularities, you affect the gauge dynamics. So it's a bit like geometric engineering of CFTs. But since what we have is a compact space, you need to be careful with the flux that you are turning on. They have to cancel appropriately, and there's a finite set of possibilities. And these here are just ADE singularities on the K-tree manifold, and this gives you just the consistent, the consistent choices of singularity freezing. What you end up with then is a picture like this, which is now the abstracted out figure of what is the result. That you have a component here, a moduli space that's characterized by having a maximal rank, and then you have maps that go to all the other ones. I want to emphasize that you recover really every other theory that has been constructed in this regime in different duality frames, things like that. And when you do it actually a bit more carefully, you see that there were other theories that were not in the literature, but okay, the map actually works, also including these things that have these discrete parameters. And this is just the form of the model space, and these theories are characterized again by this discrete data. So you kind of have this unified picture. Yes.
The three new ones that you found, these are all in F theory, or do you have a heterotic realization of any of them?
So heterotic, these ones are heterotic. They are realized by triples. These ones are not heterotic. And these are realized by F theory. So if I go to, I don't know how fast I can go. Here. Right, here in F theory. So there are these three rows. And the first row is the ones that I had to above that because they have a K tree and they have heterotic realizations. These are the ones that were in that column to the left. And then these are the other three ones that have the discrete angles. You can get in F theory. Just not, I don't think. Actually, not sure if you can get them geometrically. No, I don't think so. You have to turn on Ramon fields. There is no proof that there is not anything else, but it's striking that everything that we have been able to construct is arranged in this way. So if there was something else, it's going to be very exotic. That would be very exciting to have, but I think that's realistic. So before going to the six-dimensional case, just a brief recap. You have no abelian gauge symmetries that are encoded in sublattices of the Lorentz lattice. Okay. This is just the form, moduli space, and for 1, 2, and 3 dimensions, there are maps that act on, and I give you some microscopic explanation for that, like crossing singularities and things like that. Wow, okay, so what about 6 dimensions? If you do a formal generalization of these lattice and then techniques, you're going to get something that looks like this. You have a gauge symmetry group. You see that the map is only going to work if you have a fundamental group here, not real fundamental group here. So this is one example. And then you say, well, I apply that and I have spin 17. I count my rank. So this is rank 16, this is rank 8. So I reduce by 8 and I get a new component with rank reduced by 8. I pick another group and now it has a set tree. It's E6, E6, E6. And I apply my formal procedure, I get G2, 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 so I reduce the rank by 12. This sits in a different component space. You can then look at every possible pi1 that you can get. So the transformation again is determined by this element of the fundamental group, and it maps to a certain moduli space. So if you have classification of gauge groups, that automatically gives you a classification of those fundamental groups. And then you could hope that that's going to give you classification of the moduli spaces. But again, as we saw, we can do this. We have a finite way of solving these problems. So then the whole thing is in some sense solved. You just have to look at the classification that you had before, look at the pi ones, and apply this procedure.
Excuse me?
Yes.
I'm sorry, but I came in late. Can you say very briefly what this map is, or?
What?
Well, you said there's a map that acts on
Yeah.
active load. I'm just wondering, what is the map?
Yeah, exactly. So that's kind of the whole point of the talk, because there's a version in higher dimensions that is just a realization of the effect of having frozen singularities on a K-tree manifold in M theory. And so you have your gauge symmetries, you turn on these fluxes, you see how it works, you get a map. But that same map, you can recover it without thinking about M theory, because you go to a dual frame, like a perturbative string. You work out the spectrum of that theory, you work out the spectrum of other theories that you can relate, and you recover exactly the same map. So let's say that on the perturbative side, you can.
So there's a map
Yes.
that goes to a dual that has a K3 with a frozen singularity.
Oh. Oh,
But now you're somehow getting rid of the K3 and still have the map.
Yeah, maybe I didn't understand correctly the question. What the map is actually doing is that it is acting on the spectrum of a vacuum in one component of the moduli space. It takes the gauge group, it gives you a different gauge group, and that one is the gauge group of a different vacuum in another component. So the map is related to different string vacua, one of which has the gauge group with the smaller rank. And if you apply the map in a general way, you are able to take your like subspaces characterized by some generic group from here to this other space, to this other space, to this other space. You do it systematically.
I understand what it does. I just don't understand what it is. I don't understand how the map is defined.
Physically, mathematically,
Either.
what the map is as a function is a map that is acting on the gauge group of a string vacuum, is producing the gauge group of a different string vacuum.
No, I know, but normally when we define a function between two spaces, we say exactly how the function acts. I can take, you know what I mean? Or how
Oh,
it
you
rises
mean because I just given you an example of the map acting on a gauge. What's the general form?
You gave me a bunch of examples, but you
Yeah.
didn't tell me how the map was.
Oh yeah. So it's maybe here. Where is it? That's what the map does. Take the linking diagram of the group. Look at the extended linking diagram. Look at
You
the
fold them by the fundamental group, you fold them by the center of the gauge group.
Yeah.
Okay, thanks.
Yeah, sorry about that. Yes, that's right. This is just a table with when you apply that map, you can also act on the lattices of electric charges in your theory. And this is just a huge table with what are the predictions for those charge lattices when you apply. But let's go back to what is the map, what's the nature of that map. And this is the way in which it acts. This is the way in which you have a set 4, set 5, whatever, you do this procedure and you're going to get some group. But this map actually it appears in many other contexts, and already in 97, Christoph Schweigert found that map studying flat connections on G bundles over a torus. So flat connections that are like topologically non-trivial. So you have an action that is reducing the rank of your gauge group. And that's interesting. So I'm looking at 6-dimensional theories. I find that this map is there, but also this map is here for gauge groups over T2. What that motivates is to take that theory that has this gauge group, like for example the spin 32 mod set 2, and do the following construction. So you compactify the theory on a torus, and this is the gauge bundle over the torus, and you turn on a Stiefel-Whitney class, on the torus, valued on the fundamental group of the spin 32, and that's going to produce, in this example, it's going to produce something like SP8. But in 4 dimensions, with 16 supercharges, there is only the Montenegro duality. So you have this strong weak duality that has an action, a specific action on the gauge group. It trades short roots by long roots, and you get precisely spin 17. So far, I have a procedure. I have a 4-dimensional theory, okay, with the gauge group that I actually want. So it works up to this point. And then there is the non-trivial step that would be necessary to justify why this map is there, which is that when you go to strong coupling limit and you trade your electric charges by magnetic charges, you have your T2, you're going to see a T2 that doesn't have a Stiefel-Whitney class turn on. It's trivial. What that means is that you can now decompactify it, get rid of it, and go to 6 dimensions and have a different theory than the one that you started with. It would realize this map exactly. Okay. And the upshot is that you can do that if you look at the discrete data defining each one of your theories. So briefly, to that trivialization of the W2 going from here to here comes from a combination of 2 results that are at least as I understand it, as I am able to show that this has to work, do it at the level of the lattices. So the first point is, what is the action of the W2? And just giving that particular example of the W2, it works for other cases, but what's the action on the lattice of the non-line lattice? So I take the lattice, I separate it into two parts. One is the 6-dimensional part, and the other is the one that is associated to my torus. When I turn on the flat connection, that's topologically non-trivial, it changes the 6-dimensional part in some way. I don't have to specify it at this moment, but it changes the gamma 2, comma 2 in a specific way. It scales it, makes it smaller. Sorry, not smaller, it adds states to it. So there's a scaling in the lattice. And then you want to go to strong coupling. And fortunately, there are some results along these lines already by Persson and Volpato from 2015. So in this article, the authors, they were studying precisely 4-dimensional strong weak coupling duality in theories with reduced rank. And the general observation that they made in a family of theories with reduced rank is that there is an operation that you do on the lattice, which is as follows. You take it, you dualize it, you take the dual of the lattice, and then you scale it. In this particular case, you dualize it and you scale it by 1/2. So if you have this gamma E prime, which is this original lattice here, it's going to transform like this. If you take the gamma 2, comma 2, and you dualize it, and you scale it, you go back to gamma 2, comma 2. So you have a gamma 2, comma 2. And then the other part, it transforms in some specified way. I'm not specifying that. It's going to define the other theory. So, but the point is that you turn on the holonomy, then you do S-duality, and you go back to your original gamma 2, comma 2, which one can identify in the context, for example, of doing perturbative computations. You can show that gamma 2, comma 2 is to be identified with the torus without W2. So the thing that we wanted, it actually works, and it works in all the examples that I have checked. So the T2 is trivializing, the gauge model is trivializing there. So actually what happens is that's absorbed by the 6-dimensional internal space, the S-dual theory. And the same procedure, it applies to other kinds of flat bundles that are necessary to define all the other theories. So in this sense, you get a justification for this construction in full generality. And in the last 10 minutes, I want to exemplify this in a setup that is slightly simpler and perhaps more representative of why this works. So I'm going to go back to 9-dimensional theories, where I only have 4 theories with rank reduction, apart from the main components. And the goal will be to recover each one of them using this procedure and try to give you some explicit way in which this works. So the first one is the CHL string, the one where you take the 2 E8 factors and you got diagonal E8. That's heterotic string. The other ones are type 2 strings, and this is, you start from the type 2A or the type 2B, and you do a particular asymmetric orbifold of that theory. You turn on a particular holonomy that breaks supersymmetry in an appropriate way, and then one of them you can turn on a discrete theta angle. So how does this work? Let's do CHL string first. So start with the heterotic string and put it on a circle. Only a circle. Actually, you didn't need to turn on holonomies or anything like that. You just start with a circle, and you have, if you have an E8 factor, that's enough. So we can, for simplicity, just take E8, E8. Okay. Now it turns out that so we have to compactify down to four dimensions. So you put the theory on a T5. So compactify on a T5. There is a holonomy quintuple, which is just a flat connection on the T5 that completely trivializes the E8. Okay. And so you killed an E8. And then you go to strong coupling and you decompactify. So the same thing as before. And this is the sequence of transformations on the lattice. So you would start from, this is the Narang lattice. This is the gamma phi of the torus. Then you turn on the quintuple, it's going to scale it. And then you go to strong coupling, it's going to give you gamma phi. And this resulting lattice here is just the lattice of the CHL string. So you decompactify to 9 dimensions, you get the CHL string in a kind of indirect way. It's starting from a quintuple, but you have the CHL string here. So this is kind of roundabout, but this generalizes. It not only generalizes, it also tells you very explicitly that the way in which this works is by deleting an E8 group, because the holonomy is killing the E8, which is something that you don't see from the CHL.
So, let me just understand the decompactification step. So
Yeah.
you go down on T5, you turn on the quintuple, and what's the step that lets you get back to gamma phi again?
Here,
Strong
right.
coupling.
Yes, this is the generalization of this transformation here. So in this example, you started with gamma 2, 2.5, but it can be gamma 5, 5.5.
Oh, you say it's an S-duality in 4 dimensions?
Yeah.
So the S-duality in 4 dimensions I see. Oh, that's,
It transfers the quintuple into the holonomy. And you could have done it backwards. If you started from like put T5, put the CHL holonomy, you would get the quintuple as a result. So, what about the asymmetrical ripple of type 2A? This is now a type 2A string. It's not a heterotic, but we start with the heterotic. Again, it's 1. But now you have the 2 E8s, and why not turn on a quintuple on both E8 factors? You can do it, certainly. So you kill both E8s. And now you have a transformation like this. You have your gamma 5 again. So it's the same transformation, just now you kill both E8 factors, so you get this thing here. And that's the strange lattice for the AOA. This duality between this type 2 string and the heterotic string was already known from 97 in this article by Gregory and company. And so this is just so it's a verification of how this thing works out well. And you can repeat the story with the AOB, but now you start from the other heterotic string, which has a different gauge group, and this guy also admits a quintuple. It admits a quintuple on T5, and the computation is exactly the same. And you can see explicitly that it's going to go now to the type 2B asymmetrical ripples. So we recover these guys. Then there's something a bit more tentative. I think it works, but the theory is a bit more funny, which is to turn on the discrete angle, starting from the heterotic string. But the clue here is that you can, if you compactify in a circle, you can turn on a gauge field on that circle that's going to transform your gauge group from spin 32 mod set 2 to spin 32. But the spin 32, it also admits a quintuple, so you can turn that on. And if you see carefully how the lattices transform, how they are affected by these operations, you end up with a lattice that corresponds to the theory with a discrete angle. And it also seems to account for the different features of that theory, namely that this is a subtle point just mentioned, which is here I had gamma 5, gamma 1, and I identified this guy with a torus. But when you have a discrete angle, that's no longer the case. I identify this guy with a T5 because there are extra states that are non-BPS that are extending the lattice. So here the game changes a bit, but that is consistent with the fact that there is a discrete angle. But the option is that this thing is consistent. Yeah. So everything seems to work fine even if you account for these theories. And there are no quintuples that you can use to get new theories. So you classify 9-dimensional theories in general. I mean, this is perturbative computation. So, sorry, this is the computation for perturbative strings. You recover this thing, and then you can do the same thing in 8 dimensions, 7 dimensions, and so on. So this works very well. And so let me just finish with some comments and a bit of an outlook. As I said, this works for dimensions 9 to 5. In dimension 6, I think we have a good classification scheme. In 5 dimensions, we don't. We don't know all the theories that you can get. But this scheme gives you a stepwise procedure that you can use to actually classify them. You would need to classify certain holonomies that you can get in 5-dimensional theories. So that's something that needs to be done. 6 dimensions and higher will cover everything that we know. In 4 dimensions, the procedure breaks down because you can no longer say, I'm going to compactify to 4 dimensions. No, the thing doesn't work. And there are many other reasons why this doesn't work, but I don't know what's the really physical low energy reason why something like this doesn't make sense. It is something that still would need to be pinned down. And for all the future work that is more concrete, perhaps, is that you can ask how this map is realized microscopically in each frame. So, for example, you can have geometry singularities of the kinds that I mentioned, but there will be other kinds that are more exotic that are needed to fill in the classification. This is we're going to give some examples in my article with Ethan, but certainly there are other ones that we cannot pin down yet, but they have to be. And then a more tentative question is this thing generalized to setups with less supersymmetry? I think it does. There's evidence that the generalized to setups with no supersymmetry at all, but they still would need to have some underlying symmetry. I don't know what it is, but certainly the story shouldn't stop here. Okay, so that's okay.
Any questions for Hector?
Let's back up. Let me back up. Okay, so AOV is the same story that's been 32. Use the quintable again. Yeah. Yeah, I see. I see. They're coming down. They're coming down to 5. It's still incomplete, I guess. Yeah, I guess we don't. Yeah. Okay. So the picture is just So wait. So when you're thinking about going to lower Susie, are you thinking about things like doing something similar with heterotic on K3 maybe, and starting from there, or
what I have in mind is that in some cases you have the for example, if you think in terms of identicals, you can see how all of this works out exactly, how you produce positively charged identicals. But then you can have configurations where the default planes are not mutually BPS, and that breaks supersymmetry. But then you can ask if okay, I go to strong coupling, I still have some ways. I still know how the defaults transform, and I can kind of trace that behavior. And in some theories that formally makes sense, like Sugimoto string, for example, Sugimoto would be an example of that.
good. Let's see.
Any other questions? Now let's thank Hector again.